Well, it's March 6th, 2023, and we're here at the Frio River in Garner State Park in Central Texas to diagnose the continental terraforming of the true ancients who built the continents in the distant past using crystalline minerals to create concrete that would compose features like riverbeds, creek beds, hills, and mountains. Now, I've talked in many videos about the mix of 45-degree angle lines, 45-degree angle sectioning. For instance, this line right here that goes at a 45 to the flow of the river with 90-degree angle sectioning, which go at 90 degrees to the flow of the river. But I've never seen a more clear example of that mix. Here it is, and it's like etched. It's so strongly etched and strongly made. All of this concrete is so strongly made with such clear lines. My gosh. So here we have that 90-degree line, right? 90 to the flow. And here we have it meeting the 45-degree line, 45 to the flow. So there you go. So the primary lines of construction are 45 degrees, but then you'll also see 90-degree angles. All right, here's another 90 degree that's parallel to that one. 90 degrees to what? To the flow of the river. 90 degrees, okay? 90 degrees, and here's it where it meets the 45. So you see that angle, right? 45 on the right, 90 right in front of us. Interesting. So we have other angles as well, but the primary angles are 90 and 45. So I don't know how many times I've said this in terraforming videos on 3 continents, that the 45-degree angle in the riverbed is the primary line of construction. So here it's so clear. Now we're not in the bedrock layer. There's silt covering the bedrock layer right here, but in the layer above, so in this quite thick layer of concrete above, we can see the lines of construction. And in this layer, as evidenced by the material itself, not by just me talking, a 90-degree angle to the flow of the river mixed with a 45-degree angle to the flow of the river, and that meets another 90-degree angle to the flow of the river, which meets 2 more 45-degree angles to the flow of the river, okay? Now, geology is not doing this, okay? This is a reverse 45 to the flow of the river. It's meeting a 90-degree angle to the flow of the river. Here's the standard 45 to the flow, and that's, see how that meets the reverse 45 to the flow? Here's the reverse 45 to the flow of the river. It's got the 3 lines, like an arrow pointing. Isn't it wonderful? Pointing all the geologists to the fact of terraforming. Where are the geologists? Let's look for the geologists now. La-da-dee-dee-dee. Well, we see a long, straight 90-degree line to the flow of the river. But we don't see any geologists. There's not one out here. There's not one. Here's another 90-degree line to the flow of the river. Next to another one, next to another one, next to another one, next to another one, next to another one. And here's where it meets. Here's where these 2 seams. These lines are seams in ancient concrete, and that's where they meet. That's where that one meets the 90-degree. Oh, and that one goes, there's another reverse 45 parallel to another reverse 45, but oh, it takes a little dog leg. Boom! Which goes nowhere, just disappears. Oh, must be natural. So this is the clearest example. Now we have the pointing inward of the concrete that's left. These sections that are left that haven't been broken out are pointing across the creek. This is always what we find. Always what we find. They're pointing across. You've got this angle. Now in this case, you've got a right angle, a 90 degree. So you don't have the usual arrow like here. You've just got the 90, so you've got half of a triangular feature. Here's a more standard one. This is kind of standard. These are mostly right angle, right angle, right angle, right angle, right angle, and so you got a right angle and you got a 45 to the flow on the left, so you've got sort of a half of a point. Here we have two, let's see, what do we have here? It's hard to tell what we have, but you can feel the pointers telling you that this is construction. Let's get down a little bit more inside the building itself. We're inside the ancient's building and we see there's really strong seam going all the way through the material. It's not just a crack in the top of the material, it's going all the way through. So they built the section on the right. How many times have I said this? 200? I don't know. And then they built a section on the left. Geology will continue, but it's not geology. The University of Geology will go for decades until people come to terms with the obvious. How do you find the obvious? How do you discover the obvious? Well, you ask the question. It's a real simple question that's never been asked by any geologist in history. Is what I'm looking at natural or artificial? Is what I'm looking at natural or artificial? All geologists know. Their premise is that all of this is natural. How do they know that? Because a deeper premise is that we are the first advanced race in the universe. We're the first race to raise our heads above the muck and mire and achieve self-awareness. So we're the first race in the universe as far as geology is concerned, geologists, as far as any earth science is concerned, as far as any planetary science is concerned, as far as any astrophysicist is concerned. We're the first advanced race in the universe, okay? Therefore, everything we see in the universe must be natural. It must have come into existence through natural forces. Did natural forces make this integral seam in this concretized limestone? Did natural forces make this integral seam? Not a crack, not a fracture. It's not breaking apart. It's being joined together very, 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 very strongly. These were made to last the ages. All right? These sections were made to last the ages. That's why they're joined so strongly. So let's get inside the material. Okay, here's the seam. La-da-dee-dee-dee, between two sections, section on the right and a section on the left, and they joined them together. This is not natural fracturing. This is not a natural break. It's a seam, like a seam in a garment. And here's where it joins, just by chance, another seam. And that, under those pine needles, joins this seam right here. So 45s join 90s. All right? Here's the 90. La-da-dee-dee-dee. So is this a line, let's just call it a line for now, that came into existence through natural forces? What natural force is making a straight line that's not cracking or fracturing, but just existing through super hard, dense limestone? There is no natural force that does that. No natural force is making any of these lines. The chance that this corrugated, you notice the roughness of the top to slow down the water. It's not sedimentary whatsoever, although it's called sedimentary, but it doesn't exhibit sedimentary features. So this corrugated, deeply gouged material. Not gouged by erosion, gouged by the people who laid it down. Came into existence in the sections that we see it, with the section lines that go for 30 meters through extremely hard material with no cracking or fracturing evident, but just strongly joined sections. The chances of that happening naturally, just occurring naturally, the chances are zero. Why? Because we see that it's artificial. We understand that the diagonal sectioning of the true ancients who built the continents was used for strength to keep their foundations for hills strong. This isn't just a riverbed, it's a foundation for a hill. That's what riverbeds are and creek beds. They're foundations for hills. They're concrete foundations for hills. So they built their mountains from the riverbeds and creek beds up. All right? So the building of the creek beds and riverbeds, the foundations of everything else, of all the other features on the planet, had to be strong. This had to be really strong. That's why they used the diagonal feature, 45 to the flow. They did mix their 45s with right angles. I've said that about 20 times in videos, maybe more. But this is, as I mentioned, the most clear example of that. Now this takes a slight dog leg, and it's weird looking. Must be natural. So, with all of the evidence, the pointing inward, the pointing across the creek of these sections, right? The insistent seams that are not fractures or cracks by the evidence. Let me do a little expose on joints right now. Geologists will talk about joints. Now, when I talk about seams, I'm talking about a feature of the continental concrete that is the joining feature. So the seam joins the two together, just like in a garment. Two pieces of a garment are joined by a seam. So that's exactly what I'm talking about when I'm talking about seams in ancient concrete. That's where they were joined, because these structures are sectioned, yes, but they're meant to stay together. The sections are meant to stay together to form a riverbed or creek bed or a mountain or a hill. So geologists do talk about joints, but every joint is, by definition, in geology, a fracture. Every joint is, by definition, in geology, a fracture. Every joint is, by definition, in geology, a fracture. So every time that a geologist says a joint, it's a joint. He means a fracture. He means a natural fracture that's occurred through time, naturally. He does not mean a joint made by, let's say, a cosmic carpenter. Now, I look at the ancients, the true ancients who built the continents, as essentially carpenters. They're using geometrical construction just like a carpenter does. If you went to a carpenter and said, I would like a joint fracture in this part of my table that you're going to make for me, he'd say, you mean a joint, right? Not a fracture. No, I want a joint fracture. He'd say, what are you talking about? I don't make fractures, I make joints. Right? There's all sorts of different kinds of joints you can make to bring together two pieces of material. And I would never in a million years call them fractures. I would never call any joint a fracture. That's what the carpenter would say. But geologists are telling us that the cosmic carpenter, or carpenters, which they call nature, built the continents with fractures. They call them joints or joint fractures, but every joint is a fracture to a geologist. So I want to make that clear. When you hear the word joint, you're like, oh, thank goodness something's joined together. I feel safer. That's not what they mean. They don't mean something that's safe. They mean something that's breaking apart. That line is indicating weakness. Whereas these lines, which we have explored, these lines indicate strength. So there's no space whatsoever between these joined sections. No space. None. And this straight line keeps going and going and going, and geology has no explanation for how a straight line occurs in this material. Only horizontal straight lines can be explained by geology. Vertical straight lines, and we saw by getting inside the material that the vertical lines go through the material, they're not just on the surface. Vertical lines have no business being in naturally formed material. There's no way to explain this, and yet they just say, it's a fracture. Really? That's a fracture? Really? You think that? That's interesting. I've just put you in a mental institution. How weird a life would you have had to conclude that that is a fracture? Well, I'll tell you how weird it was, because I had the same life. I went to geology class too. I went through the same indoctrination camp you guys did. That's how weird our lives are, that we believe all this. That we believe that this, which leaves a regular side in this otherwise corrugated material, really rough up here, and suddenly the section faces are much more regular. So, weird, right? You can see the depth of that line. So, we can only look at the evidence, and we're going to move a little bit downstream and look at some more features. I have no idea what I'm going to find because I've never been here before. Okay? We're about 40 meters downstream, and let's just see what we can see. Let's not call these lines anything right now, all right? Let's not call this line anything. Let's not call it a seam. Let's not call it a joint. Let's not call it a joint fracture. Let's not call it a fracture. Let's not call it a crack. Let's not call this line any of those things. Let's just call them lines and just see what we see, okay? All right, so this line goes at a 45 to the flow of the river. This line parallels the river. Let's go back to this one. And this line parallels, oh, it meets a 45 to the flow. Interesting, huh? Well, there you go. Nice vertical side there. I wonder how nature did that through horizontally laid sedimentary material. Perfect 45 to the flow of the river, and that meets... Oh look, they did a little dog leg here. How cute. Isn't that cute? And this line keeps going, this parallel line keeps going. You can see it, right? I'm not playing any tricks on you. And here's the smooth regular side. Right, the regular side and the corrugated rough material on the top. I wonder why this side is different if this is so corrugated. If it just came into existence naturally, obviously this would be corrugated as well. It's not. The sides are always more regular. They should be less regular because these sides are supposed to be, this is supposed to be a crack or a fracture, this line. So that should be really irregular, but it's not really irregular. It's nothing of the kind. It's the right side. It's the ending side, the ending face of a section of concrete that was laid down in a moment by advanced races, okay? That's why it's more regular. But it's not perfectly smooth because a perfectly smooth side would then slide in an earthquake. You don't want your sections sliding against each other. You want roughness in between your sections, some kind of roughness. The true ancients could have made all these sections super smooth. They could have made all these sections super smooth, but there is a knobbiness to it, okay? See the knobbiness? So it's slightly knobby. That's because they wanted their sections to rub against each other and create, and have friction as they moved to keep the hills in place. So here's a line that just goes and goes and goes. It's 45 to the flow of the river. Straight line. Geologists don't care. They're like, just don't look at that straight line. Don't look at the regular side that's different from the corrugated top. Don't look at that. just keep repeating what we tell you. What are we telling you? That it's all natural. When the evidence supports the continental terraforming theory. Okay? The evidence supports the continental terraforming theory. Here's another 45-degree line. 45 to what? To the flow of the river. Alright? And this 45-degree line parallels the 45-degree line next to it. See this one? So this one parallels this one, and that one parallels this one, right? And let's see, all of those parallel this one. So they're always building in essentially triangles or with parallel diagonal lines. Diagonal to what? To the line between the hills. What is another way of saying the line between the hills? The flow of the river. The flow of the water follows the line between the hills. So they wanted to make sure that their hills had a good foundation, and that's why they used diagonal construction. We wouldn't use diagonal construction, and our concrete would be gone in 100 years. Well, this has been a lot longer than 100 years. Staying strong, staying integral. Nice, rather smoothish, or let's say regular side, right? Compared to the mottled top. Smooth, not perfectly smooth, a little bit rough, but more regular than the surface. That shouldn't be the case, because all of the sides of this are supposed to be, according to geology, the result of cracks and fractures that happen later on. And those should randomly move through the horizontally laid material. So these regular sides alone tell us that this is not horizontally laid material. In other words, it wasn't laid day by day, week by week, month by month, year by year, century by century. We'd have a flat top if it was sedimentary. And you say, but it could have been modeled over time. Well, limestone is famous for its mottling. It is. And yet we have to ask ourselves, was it mottled by water over time, or was it laid down, mottled? And you say, what about all those caves that are clearly natural caves? Oh, well, are they clearly natural? I would suggest that none of those caves are natural. None of those limestone caves are natural. I suggest that those caves in limestone across the world, and using other materials across the world, were created, in fact, were left as empty spaces in built structures, built continents. So nobody was digging out the caves. They weren't naturally created, they were artificial. And they were simply left as empty spaces in built structures. So here's the 45 to the flow. You can see it in the water here in this nice slow moving section. And there's a parallel 45 to the flow. Okay? It's stepping up as it goes down. That's interesting, huh? Stepping up as it moves downstream to slow the water. That's why the water is moving slowly. Also the degree of the I mean, they wanted their hills to stay, so they kept their water courses at a shallow degree. 1 degree, 2 degrees, 3 degrees, whatever it is not important. What's important is that they wanted to make sure that the water did not go fast, so they didn't create, in general, steep major river beds. We have different sized sections, right? Here's a rather smallish section. Here's the edge to this section, right? I mean, smallish for the true ancients, not smallish for us. This is huge for us. I mean, and here's where it gets bounded on this side by this line. Their seams are so integral that it's hard to see them sometimes, especially on the camera. But it's easier just with the naked eye. But anyway, so there's that section It's about 3 feet by 5 feet, I'd say. 3 feet by 5 feet. And the next one is bigger, triangular, different shape. So they have different sized and different shaped sections. Now, why would someone building something do that? Well, for the same reason that they use rough sides to their sections, so that the section next to it, before it broke out here, right, would in an earthquake rub against this and it would stay stronger than if it just slid. So they use different size and different shaped sections for earthquake mitigation. And the pyramid builders did the same. They used different sized sections. They call them blocks. We can call these blocks too. That's what they are. Regular side, right? You can see it. Corrugated top, highly corrugated, deeply gouged, valleys, hills, massive, weird, corrugated stuff. And then suddenly, oh, pretty regular. When you see the interior faces of these sections, they're always presented as regular. So different size and different shaped sections of ancient concrete compose the true ancients' riverbed here at the Frio River. And in the words of Forrest Gump, that is all I have to say about that. Let's go look at the water. Do you think the true ancients who built the continents knew something about water? Do you think they knew how to channel it? Do you think they knew how to slow it down? You can see that this line is a 45 to the flow. See that? That bedrock line that goes across, that's a 45 to the flow. You can vaguely make out another one right there. Can you see that one? That's a 45 to the flow, paralleling the one on the left.